Hello, my name is Alapan Mukhopadhyay. I'm a fifth year PhD student of Karen Smith at Michigan. So I'm broadly interested in commutative algebra and algebraic geometry. So most recently, I have been thinking about something called Hilbert-Coons multiplicity. So what is Hilbert-Coons multiplicity? So it's a multiplicity theory in positive characteristic. So given a ring in positive characteristic and a finite column ideal, the Hilbert-Coons multiplicity is a number. The higher the Hilbert-Coons multiplicity, the worse the singularity is. So given a graded ring and a finite column homogeneous ideal in the graded ring, I have associated a complex valued function which generalizes the Hilbert-Coons multiplicity. So I call this function the Frobenius-Poincare function. So what are Frobenius-Poincare functions? Roughly speaking, so a priori it's just a limit of Hilbert series of a sequence of modules. So I have shown that not only the associated sequence of functions coming from this sequence of Hilbert series converges, but also the limiting function, which I call the Frobenius-Poincare function, is in fact holomorphic everywhere on the complex plane. Now, the Frobenius-Poincare function is basically determined by the information of a graded ring, a fixed homogeneous ideal, and the Frobenius. So in some sense, it's a finite amount of information. And this finiteness should be revealed in the structure of the holomorphic functions. So in examples, although a bit handful, I have shown that when, for example, when the ring is dimension 1 or dimension 2, or it's a polynomial ring, the Frobenius-Poincare function is just a polynomial in e power minus iy divided by iy power dimension of r, where y is the complex variable. So before working on Hilbert-Coons multiplicity, I have thought about some general questions in algebra. So what are those questions? So fix a field K and a K algebra R. So suppose that the module of Kähler differential omega r over K is 0. If additionally, the algebra is finite type over the field K, then it's a well-known result that the algebra is just product of finite field extensions of the base field. So in particular, it's reduced and integral over the base field. So I've investigated similar questions after removing the hypothesis that that the algebra is finite type over the base field. So in a joint work with Karen Smith, I have shown that if the base field is perfect, and if the algebra is just Noetherian, or if it is n-graded over the base field, if the module of Kähler differential omega r over K is 0, then R is in fact product of fields, not necessarily finite field extension of the base field. In another joint work with Shubhadeep Mondal, I have shown that if the base field has characteristic 0, and if the module of Kähler differential omega r over K is 0, then R has to be integral over the base field K. So long before that, I have worked on something called Seshadri constants. So what are Seshadri constants? So given a projective variety and a line bundle on the projective variety and a fixed point on the projective variety, so the Seshadri constant is a numerical invariant. It measures the positivity of the given line bundle on the projective variety. So I have worked on a generalization of Seshadri constants. It's called the multi-point Seshadri constants on surfaces. So the famous Nagata-Biran-Zember conjecture, it says that roughly when the number of points is large enough and the points are very general, then the Seshadri constant at those very general set of points should have a well-prescribed maximum value. So in a joint work with Krishna Numantu, I've shown the following. So first of all, we have given a lower bound, which is pretty close to the upper bound predicted by Nagata-Biran-Zember conjecture. So we have shown that either this lower bound is achieved, or there is something called a Seshadri curve, a special kind of curve with special properties on the surface, which computes the Seshadri constant. So either the lower bound is achieved, or there is something geometric happening over the surface. So when the surface is in addition to everything, a rational rule surface, we have shown that when the number of points is very large, then the lower bound we have given in general is in fact achieved. And in fact, that result verifies the Nagata-Biran-Zember conjecture, but in an asymptotic sense. That's it. Thanks for listening.